All right, let's focus, please. Hey, everyone, let's concentrate. So yesterday I talked about concavity. I talked about point on inflections and stationary points. All right. Today we're going to use the knowledge we have. What is concavity, inflection, and stationary points? We're going to use it to analyze the gradients of certain curves. All right, or any functions that we need to learn. So, by the end of this lesson, I know why. It's fine. You should be able to sketch curves using significant information about the first and second derivatives. Use a second derivative test as a test for the nature of a turning point. All right, it will make life a little bit easier compared to using the sign test. Determine the critical features of a function algebraically using calculus technique. Determine the coordinates of local and global extrema over finite domains for the graph of a given function. And finally, distinguish between the purposes of a sign test, second derivative test, and the concavity test. All right?
Yes.
Now, let's start off looking at this question. Is it correct to conclude that if a function fx has first derivative is 0, second derivative is 0, then there must be a horizontal point of inflection at x equals to a?
No. Because there
You've
could
got
be
a
a
sign
turning
test
point.
double derivative, don't you?
Well,
Could be turning point.
let's look at it this way, all right? Could
Can
it
be
the
inflection or turning point.
Now, I'm telling you that this is 0. So I've got fx. Oops. Let's
Because if you do
wait.
x to the 4,
I've got
then turning point.
that. Doesn't work.
Or x
I've
to
got
the 4,
f-
or
fx.
Oh
x to the 3.
yeah, because you got
Or
a sign
x to the
test.
4.
Any
Double
function.
derivative, don't you?
All right. We don't know what the function is,
Yeah.
but we know at a certain point.
No, I'm not believing it.
All right.
No,
F of a
don't
is
understand this
0. A equals to 0.
Yeah.
Is it a horizontal point of inflection?
Not necessarily. Not necessarily. What about x4, sir? Like Jules said.
Thank you.
Yeah. You got a
Like I
sign.
said,
You got a sign test a double derivative.
I said that first.
All right. If it's something like that,
It's x
at this point here, if I draw it properly, a.
turning point.
All right. F
But f of x.
a equals to 0.
I don't actually understand.
A equals to 0 as well.
Yeah.
Correct? Yeah? Now,
X squared even.
this one,
Anything even.
so let's say x to the power of 4.
2.
Minus 3. All right?
Yeah.
At this point here,
That's equal to
f
r.
of x equals to, that would be
Negative 3.
0.
No, 0.
That's
Sorry.
0.
Yeah.
Still 0.
Last lesson.
All right? So, can you say for sure that
No.
Bigger, like a fat.
it is a horizontal point of inflection?
No.
Yeah.
Generally, it is correct. All right? If you think about something like x to the power of 3, x to the power of 5, I would say. Generally, it's correct, but it's not always true. So you got to be thinking about look at the graph, analyze the graph. Sometimes you really have to do the sign test or the concavity
Wait,
test.
so
Yep.
is it only for even powers, or is it only for even powers, or can it happen on odd powers as well?
Isn't it only even powers though? That you would have to check for sure.
I'm actually not sure, because if you add in all the other powers for odd power polynomial, you may get something.
Crazy.
Yeah, you may get something crazy. So I can't say for sure, certain. All right.
Got weird
I mean,
shapes.
I don't see a lot of situations
Yeah,
where f second
Yeah, no,
derivative
good
is 0. Not a lot of situation I have to deal with. But
Yeah,
just
just-
remember, generally it is true if it is
Probably the
if
extra 3.
first derivative and second derivative is 0, it's generally true that it is a horizontal point of inflection. But this sort of situation, it is not. All right. So you cannot say that this statement is exactly true when you do your test.
Could that show up in exams, like where it would ask, like, is this statement true?
I don't think so.
Oh.
But like,
Don't
you're gonna
think so.
apply that,
This
right?
is-
But
this
you're gonna
is
have
food
to
for
apply
thought,
it, yeah.
all right? So that you're all aware of it. I want you all to be aware.
But you have
of
to
it.
write a statement.
All right.
You gotta-
Next. Now,
Prove that.
let's
You're
have
gonna
a
get
look at
improved
this.
statements and methods.
The function y equals fx exists such as f2 is minus 2. First derivative at 2 and second derivative at 2 is 0. And then the first derivative is less than 0 for all values of x except when x equals to 2. Right? Can you sketch something like this? If you got a graph like this, what I would do is I will start off with something like this. Put a dotted line in. Alright. So I do know that this is 2. So let's have the first look at the first statement. f2 equals to minus 2. So we know that at this point, 2 minus 2. Alright. So here it says that the first derivative of 2 is 0. So you know that it is stationary. It could be minimum. It could be stationary point. It could be maximum, minimum, or stationary point of inflection. Right? If that's the case. Now, if you look at that, you know that it's more likely this or this. Again, you can't really tell. So you have to look at the third condition. The third condition says that f of x is less than 0 for all values except x. So therefore, you know that this is a decreasing function, all right? But at 2, which is 0, here, before that, that is negative, and this is negative. What happened? What is it telling me?
Horizontal point of
It's
inflection.
horizontal point of inflection. So the graph should look something like this, right?
Yeah.
So here, therefore the graph should look a possible graph, something like this. Because it's a decreasing function, everything else is negative. Every gradient is negative,
So why
except at that point, which is 0.
So what does it
Yeah?
do?
Because it
It's
tells
like
you,
maximum or
it's like,
Sorry?
If, like,
because it tells you negative.
can't you just
negative.
know that it's
So it
a
tells you
horizontal
if
point
it's
of
an
inflection,
inflection.
because
Or if
it
it's
was
concave, or if it's...
like the second derivative of 2.
But don't you sign test the first derivative?
Not
Because you can
necessarily,
see
because
one
when you
side
have
is
got
negative and the
x
other
to the
side
power
is still
4.
negative. Or is it?
What happened then?
Because
That
like,
point
I
there,
swear like last lesson,
f
sign
x
test the double derivative.
equals to
I forgot
0.
why.
F, x, f double dash
Right, it's out here. It's right here.
So you do have to look at the sign test.
What
Right.
I'm talking about?
So here the sign tell you definitely
Look like this.
this is going to look like this because it's a decreasing function.
It's this.
Alright, happy with it?
Oh, that's just to figure out if it's an
Got it?
Yeah.
Let's move on to the next bit.
The oblique one's like.
It's like only if it's a point.
Alright,
Yeah,
I
oblique
would
one's
like
that,
all
like
of
that.
you now,
So like that, right?
without using the second derivative, can you determine the location and nature of any stationary points?
Yeah, I'm saying that it's going to be negative
All right.
throughout except the horizontal.
Please do not use second derivative. I want you to recall using sign test because you may need to use your sign test.
Why is
Sometimes you may need to use your sign test. Alright?
that's the derivative. Yeah. So it's the gradient is always less than 0, so the gradient's negative all the time.
Right? Now, if you do your dy dx, you know that stationary point dy dx equals to 0. Alright? So solve it, you know that x equals to -1 or 2. Sign test. Now I know some of you learn it a different way. I've got my way of doing it. Everyone has their own way of doing it. I like to do it this way. Less than -1. This is -1. Between -1, x and 2. 2 and greater than 2. Alright? I like to do it this way so that I know the continuation. So here, this exactly, I know this is 0. So it's
Together.
It's horizontal. Alright? So there's no gradient there. Let's think about if it is less than 1. Alright? You need to think about what number you could use. You could use -2 or -3 or whatever. So what I tend to do is I like to use a really large number. So if I use 10, this would be 600, take away 60, take away 12. So you know that will be positive.
Wait, so do you have to use the... No, never mind.
Sorry?
Never mind.
And then between there, I will use, let's say, I'll use between 1 and 2, I'll use 0. 0, 0, that's minus. Negative. And then greater than 2, I will use 10. Just now, if I use -10, I'll use 10. Minus, if it is 10, that again is positive.
Wow.
Alright? So you know that the curve looks this way.
Classic x to the power.
So this is max, this is min. Now, I've sketched out the curve there, max and min. What is it telling me? What is the shape of the concave here? Is it up or down?
Down.
Concave up or concave down?
Concave down.
Yeah?
Yeah.
It's concave up, correct? Max is
What?
concave down or up?
Down.
Down.
Yeah,
And min is concave
Up.
up. Alright? Keep that in mind because the next bit we're going to talk about how we are going to use the second derivative. Looking at the concavity and then test test the nature of the point.
Be anywhere.
Could be anywhere.
Yeah.
Alright. Now just a recall, you don't have to write this down, you'll get it in the in the lesson slide when I upload it. You know that the nature of the stationary point, minimum turning point, if you do a sign test, negative, 0, positive.
Wait, so sir,
Yep.
you don't need to do second derivative to figure out if it's a horizontal point of inflection. You can just use
You can use the sign test.
just use first derivative sign test.
Yeah.
Yeah, okay.
You can use
Yeah.
that. Or you can use a concavity test as well. Alright?
Yeah, alright.
So then the maximum horizontal point of inflection, you can see that if it's 0, both sides will be negative. Positive, 0, both sides will be positive. Alright? So either this way or that way.
Yeah.
Alright? Minimum turning point is this,
Yeah.
negative, positive. That's positive, negative. So now, like I said, think about the concavity. Alright? Because we use the second derivative to test for the concavity of the curve. So, if minimum turning point, this is concave,
Concavity test
up,
is like
this is
the
concave down.
double
Alright?
derivative.
Let's start thinking about how do we use the second derivative.
I think you'll do it.
Alright, the second derivative test. Given a function y equals fx with the stationary point and x equals to a. Then the second derivative test, it identifies the nature of the stationary point using concavity of the function. If it is less than a, the function is concave down. Concave down is that way. Correct? Yeah? So therefore it is a maximum.
So if it's
This is why you need to know the concavity before you use your second derivative.
concave down. Wait.
Alright, now let's keep that for a while. Here, if it is greater than 0, the function is concave up. So therefore, that's a minimum point. Think about when it is concave up, when it is concave down. All right? That will tell you the maximum or the minimum point. So less than 0, concave down, pointing upwards. Greater than 0, concave up, that is pointing downwards.
Wait,
so
so
therefore, it's minimum. Yep.
You know when it's like equal to 0, and
Yes,
you said it can be a stationary point.
Yep.
Is like x to the power of 4 an example of that, where it's a stationary point?
It's a minimum.
Yeah.
Because, all right. So when f double dash a or second derivative equals to 0, that's insufficient information. The point could be point of inflection or stationary point. So you need to use either concavity test or sign test. It really doesn't matter. It's up to you. So if you use a sign test, if it is a x, y equals to x to the power of 4, sign test, you've got a negative, and then you've got a positive.
Yeah.
All right, so that you know it's a minimum. All right, the concavity test, you know that the concavity test that will be negative and negative. There's no change. All right.
Wait, isn't that? Oh yeah. Okay.
Yeah. Okay. So this is generally, these are the two you should know until you come to here. You can use a sign test or concavity test. All right.
Yeah.
Next example, we know previously 2x cubed minus 3x squared minus 12x plus 4. I've shown you the sign test. All right, you know that when x is minus equals to minus 1 is a max, and x equals to 2 is a mean. All right, so let's use the second derivative there. Let's check. So here, we y dx equals to 6x squared minus 6x minus 12. d2y dx squared equals to 12x minus 6. All right, so x equals to minus 1. d2y dx squared at x equals to minus 1 equals to 12 times minus 1 minus 6. That is minus 18. All right, d2y dx squared x equals to 12 times 2 minus 6 equals to 18. All right, minus 18. Is it concave up or concave down? Concave down, so it's a max.
Yeah.
Right? Concave down, this is a max,
Wow.
and this is a mean. Makes life a little bit easier without using the sign test.
Yeah, a little bit.
But you've got to be really careful if you got 0.
Depends
Now,
how
I
easy you
would
try
say
it.
that it's easier when it comes to calculator assume section, because you can just plug into your calculator. That's all. All right? Always remember that. Plug into your calculator if you can. Use your class pad.
You can always graph
Alright.
it on your calculator.
All right, next. Now, can you determine the location and nature of the stationary points? Let's start doing the dy dx and then the d2y dx squared. Now, sometimes when you have got a division or a quotient, sometimes I like to do it as a product rule by using x equals to the power of minus 1. But again, it's up to you. All right? Is Max still in this class, or has he moved? Max?
Is he not on the road?
I don't know. I haven't checked. I just realized that he's not here, so I better check.
He went back to Doug. What dog? Dog?
Yeah.
One of the D ones.
No, he's not on the roll anymore.
How the gradient changes. Recovery is how the gradient changes.
What do you mean?
I still don't really understand.
You actually,
What do you not understand?
what is concavity? Like, I
Concavity
understand.
just means like U or N.
Huh?
Concavity is just if it's like U or N.
No, I know, but like, you know how what is like concavity like here?
Yeah, please move to Mrs. Smith.
That's what I don't get.
Like,
So like, say if you have like an oblique point of inflection.
Yeah, so here is concavity. Here the concavity
is down.
down.
And then as soon as it goes to here, it goes up. As soon as it hits the inflection, it goes up.
And here it's just
Why does the second derivative show concavity?
Oh, I don't know why. It just does.
second derivative.
So it's concave. It's concave
So
down.
you should be able to do the first derivative and the second derivative, alright?
Oh, this is concave down. Yeah, so that's why it's possible here. When it's there, it's concave down. That's what I mean. Yeah, okay. And here it's concave up here. Okay, it's negative at this point. Yeah.
So it's up here, positive, positive, and it's negative, negative. This is the point of inflection.
And when it goes here, it goes positive. Alright, well.
Between 0 and 2, the concavity is negative, so it's negative.
Alright,
That's why if it's 18, it's negative 18, it's negative. So it's minimum.
Yeah. Understand. No, if it's negative, then it's concave down, right?
Yes, positive.
Yeah. But the max value.
When you're doing the second derivative, think about situation like this. Perhaps sometimes it's easier if you actually expand it
I was stuck.
and you've got x squared minus 1 as the numerator. Alright? So,
different
you
answer.
know a stationary point.
Yeah, I got negative x squared.
Yeah, that's what I got.
Yeah.
dy dx equals to 0, correct? Now, x squared can never be equal to 0. Agree?
So,
Because if it is 0, it doesn't happen.
so
Yeah.
Yeah?
second line of working, you had the +1 instead of -1 when you factorize it out.
Yeah, so x minus 1. So I've got
Oh, wait.
the square is out. Taking it is plus 1. Alright?
Yeah.
If I take minus x minus 1 squared,
Yeah,
which is
no.
minus
Yeah.
x minus 1, x minus 1, correct? So if I take one of that out, it's minus x plus 1. Alright? Got it? So therefore, you know x squared equals to 1, x therefore equals plus or minus 1. Alright? Agree with that? So you know that x is plus or minus 1. So let's do the 2y dx squared, which is x to the power of 4, 2x times x squared minus 2x x squared minus 1. Alright?
No, because it's using chain rule.
Yeah? So once I work everything out, it becomes 2 over x cubed. Now, substitute in dy, d2y, dx squared at x equals 1 equals to 2 over 1, which is 2. d2y, dx squared at x equals to minus 1 equals to 2 over minus 1, which is minus 2. So therefore, this is the mean, this is the max. Alright? Now, strictly speaking, I should work out the y coordinate as well, which is, yeah. So, the coordinate, so when x is 1, 1 minus 1 squared is 0. So x is 1, y is 0. And when x is minus 1, minus 1 is minus 2 squared. Minus 2 squared is 4. 4 divided by minus 1 is 4 minus 4. So that point here, that's minimum, and that's maximum. Alright? So the location, you should always look out the
What line
coordinates.
of work did you use? So did you use quotient rule there?
Sorry?
Did you use quotient rule?
Yeah, that is quotient rule.
I use quotient rule.
So why did you differentiate?
I differentiated this.
Oh, my bad. Yeah. Okay. I
Alright.
did it wrong. I did the wrong steps.
Yeah,
Wait.
it's very easy. So, alright, everyone, you got to be really careful when you look at the
Did you?
derivative. So you always start off with this, and then that. Now, because I did it, I started with dy dx first, and then I do that. Sometimes you refer to the question. So sometimes you got to be really
No,
careful
I
when
did
you do a
the.
question
I
like this.
differentiated the bottom function, the bottom one first. So the other one was negative.
Yeah.
So yeah, that's why.
All right. Let's look at example 3, I think.
Nah, he got it right. That's right. It's cool, great. Nah, he didn't. He used his quotient rule straight away.
All right, example 3.
That's the whole point of quotient rule, where you have a function over a function.
Let's do example 3, please. You need to be able to sketch it. It's really interesting, this one. What I would do is looking at a question like this. The first thing I would do is straight away derive dy dx, which is 12x squared minus 4x cubed. Alright? And then I derive d2y dx squared, which is 24x minus 12x squared. Alright? I mean, really doesn't matter. You can do that straight away, or you can do dy dx first, and then do your d2y dx squared. As long as you're careful. So looking at this, you know dy dx has to be 0 at stationary point. Right? So I get x equals to 0, x equals to 3.
26 minus. Throw the power of 4. Anyone. Yeah.
So you know that when x equals to 0, it's actually the y-intercept, correct? Yeah? That's pretty much straightforward. You should know that looking at that. So the y-intercept is one of the points, whether it's a stationary point, whether it's minimum, maximum, or point of inflection. We don't know yet.
Ooh.
So let's look at d2y dx squared. d2y dx squared. That's equals to when x equals to 0.
It's gonna be 0, sir.
Yep. Now, again, you don't know whether it's a point of inflection or whether it is whatever you call it, point of inflection, horizontal point of inflection, or minimum or maximum. So what you need to do is to use concavity test, or you can use your sign test. All right. If you use your concavity test, so x d2y dx squared. So you know at 0, that's 0. Less than 0, greater than 0. All right. If it is less than 0, let's say I use minus 1, minus 24, minus 1 square is 1, so it's minus 12, minus 36, that's negative. If it is 1, 24 minus 24
12.
times 1 minus 12 times 1, which is positive. So it is a point of inflection.
Horizontal.
It is horizontal point of inflection. Or you can use the sign test. If you use the sign test, x dy dx
horizontal because remember,
Negative.
it's
less than 0.
No, but it goes negative.
Greater than 0.
Okay.
So if it is
Down
less
here,
than
and then
0,
here,
it will
here.
be
That's zero.
positive,
X equals 0.
Oh, right.
and it's positive.
Yeah.
Alright? So it is up to you. You can use your sign test or concavity test. So you know that at that point, this is the point of inflection. Alright? And the other one, d2y dx squared at x equals to 3
Negative. It's gonna be
equals
negative.
to
So it's
Did he use that?
minus 36.
Yeah.
So therefore this is max. Alright? This is point of inflection. Horizontal point of inflection. Of course you need to work out your
Wise.
x and y. So this point, straight away you know that when x is 0,
Y is negative 7.
yeah, x is 0, y is negative 7. When x is 3, y is, I worked it out, 20. Alright? So, sketching it. You don't need to know your y-intercept. You do not need to know your y-intercept. You know this is 0 minus 7.
You don't
And then
concav
this
the
point
other.
here
So
is
you've got to
3.
3, 20.
like a sign test.
So it goes like this.
Yeah, how you did it.
So you just set it up like a normal sign test, except the bottom is a double driven.
It looks something like this, alright? I mean, my drawing is pretty bad. So this is the point of inflection. This is the max. Alright?
Now, if you were to draw the
Use
graph,
your understanding. Use your understanding of first derivative and second derivative to actually sketch
shove
it.
into there, and so like what -1 and then +1 together. Yes, that means that it's concave down here, like that, concave down, and then changes here to concave up.
Now,
Graph that looks it's a horizontal.
the next thing,
The other way.
what I want to look at is thinking about the global maximum, the global minimum, local maximum, and local minimum. Alright? Let's have a look at the next slide. Here,
The gradient.
you must be able to know where the local minimum
This
is,
is a gradient.
where the local maximum is, where the global maximum is, and global
Yeah,
minimum
there's 2 tests
is.
you can do.
Alright? Now, think about the graph that I've given you there. Here,
One works.
Local.
I've defined it as a finite domain. From here to here.
Oh, yeah.
I did not have any arrow.
It's already negative, so
Yeah.
Alright?
max.
That's definitely a finite domain. It's
okay,
not going to
yeah.
infinity. So,
Sub it into double.
the local maximum.
Yeah, and then you get like negative.
The
36.
local maximum is actually looking at here. Localize this point.
Which means the max.
This is your local
Maximum.
turning point. Alright, local maximum.
Global is the one
Alright.
all at the top.
And then think about the local minimum. Here, this actually is the turning point. This is the
Local, and
Local.
global.
minimum. Alright. To check your global maximum and global minimum, you need to look at where the domain finishes and where the domain finishes. Alright, those two.
Start with finish.
So here you must work out what this coordinate is, and you must work out what this coordinate is. Alright? Working out this coordinate, you know that this is not the minimum
Also 4.
because it's actually the position is higher. So therefore the local minimum here is the same as
global.
global minimum. Whereas this will be the global
Maximum.
maximum. Alright? So you must make sure that you know, you must check both ends. Because if this graph were to be extended by this bit, up to here, that would be your global minimum.
Maximum here.
Right? Let's do the next exercise. The last example is a killer.
No. You don't need to add this one. Because just
That is a killer.
just stationary
It's a
point.
long one. I I wrote this example myself. It's pretty nasty, I would say. So you need to determine the coordinates of the local and global extrema, indicating the nature. You need to locate any points of inflection within the domain. Hence or otherwise, state the interval for which the function is concave down. Concave down means d2y dx squared is less than 0. All right?
Three minus two. 3 minus two is 4.
Oh my god, I'm so stupid, bro.
I mean, the first thing I do is
Extreme is the max, right?
Yeah. Well, extreme, it's max away.
Yeah, okay. I know if it's global though. Not between 2 and.
Because you just gotta check out to -2. This one as well. You gotta find the coordinates of those two. 3 times 12 take.
now you can find the two stationary points. You don't know whether, I know one is minimum, one is maximum, but you don't know whether it's a global minimum or global maximum. All right? So you need to check for the two extreme points, which is -2 and 5/4. All right?
Oh yeah, you got it there. Yeah. So just factorize it out. Factorize 6x out. 6x.
12 times 25 and 16. Bro, what are these numbers,
Yeah, bro.
man? What is the point of these numbers, sir? Stupid numbers on 25.
Hey, surely give me the answer for the. Is this this one? This one?
That's what I'm doing now, yeah.
Surely chuck me the answer after you solve this. Mate.
Fuck that. I don't want to solve this shit. You know, half that, so 125. Fuck this, bro. That makes that 6, that makes that 4. So 3 and 2.
All right, and work out
3
the
times
local
25
max, local mean.
is
Of course, if you use your calculator, it's probably
75.
a lot more straightforward. You can see it straight away.
2.
All right?
Take
Now, you need to locate any point of inflection
1, 2,
by using f, the second derivative equals to 0. Right?
32. Take 2. I've got kind of simplified answer. It's gonna be negative, I think.
Right? So the stationary point is when x equals half. So now locate any points of inflection within the domain, so you know that there's only one point, because the second derivative is a linear equation, so there's only one point. All right?
It's equal to 111 over 32.
Why is it 0? Why is it 0?
So what you can do
Oh.
to find out whether it's a point of,
So you did 0, 0 at the top there?
sorry?
For instead of 0, negative 2, you did 0, 0, yeah.
Thank you.
Just solve back into the original equation.
Yeah.
Into
Thank you.
3x squared
All right.
minus 2x cubed minus 2.
So now
Yeah.
what you can actually conclude from here,
So that's a global.
by looking at this, you know that this one will not be the stationary point of inflection. Why?
Because it's
whole
not.
number.
Because it's not a.
It's not 0.
Not fx.
Yeah, because fx is not 0.
Yeah.
So you know
Yeah,
that it's
yeah.
not
Inflection.
stationary point of inflection,
Oblique, right?
right?
So oblique point inflection.
Yeah, so it's oblique. So you can find the point of inflection, and you know that this will be oblique point of inflection. If you don't believe me, you can substitute in to find there will be a gradient. So fx will then be equals to 6 times half minus 6 times 1/4 equals to 3 over 2. So there is a gradient. That is the oblique point of inflection. All right. So when x is half,
Wait.
Yep.
Why did you sub in this? Oh, sorry.
sorry, just to prove to you that there is a gradient there at the point of inflection. All right. That's why I substituted in to show you.
Yep. Okay.
But you can actually conclude from here that since there are only 2 points, it will not be stationary point of inflection. Yeah? All right? You know that these 2 points are the maximum and minimum. You know, therefore, that is not the stationary point of inflection. Because from here, you can only find 2 points. And with those 2 points, you can see that the second derivative, that's maximum and minimum.
I think you got your global
All right.
maximum wrong.
So therefore, you can find out the. You can find out where the interval for which the function is concave down. So concave down, positive or negative?
Negative.
Negative. So think about it. Which part of it will be negative? Which part of it will be concave down? So from the point of inflection onwards, all right, from the point of inflection onwards to the other bit, which is that bit here. So it will be half x and 5 over 4. All right. So there's a point of inflection is that.
True.
All right. So think about when it is concave down. Here, that's already telling me there's a concave down bit. So you know it's going to concave down until 5 over 4.
Yep.
All right? And then from here, you know that there's a change from there down to that bit. All right? So this will be worth 1 mark. There's probably 2 marks. There'll be about 3 marks, I think.
What?
3 or 4 marks.
That's gotta be 4 marks minimum.
All right, I'm going to stop here. I will upload the PowerPoint when I actually start writing this out again. All right? And video will not be uploaded until... Oh, hang on. There should be another slide. Sorry.
So I think the internet's working.
All right, there's another slide. This is important. All right, I totally forgotten about this. Now, this is just a summary of the three calculus tests. The first derivative test, the concavity test, and the second derivative test. All right? So the first derivative test is just a sign test. You find the nature of a stationary point, so you can find what A is. And then you use points either side of A to see whether it's increasing or decreasing. All right? And then the concavity test is where there is a change on concavity. If there's a change occurring on either side, it is a point of inflection. All right? Then the second derivative test. You can determine the nature of the stationary point, but you need a concavity test or sign test if the second derivative equals to 0. All right?
So the internet's working again.
Is it?
Yeah.
All right. All right, that's all I have for you today. Hopefully
Yay, now
you've
it's
learned
the
something.
spec.
And I am going to start.